Alright, Bismillah, quick lesson on motion in a circle and statics. So straight into it, we have motion in a circle. You're given a circle always has radius r, okay, and you form an arc based on these 2 points, A and B. How can you find this angle theta? Well, we define theta to be S over r. Okay, very simple. Equation's right here. Theta equals S over r, the length of the arc and the radius of the circle. And this is theta, not radius of, radius of the circle. And this is theta in degrees, radians. This is theta in radians, which is just another way of saying degrees. How can we convert it to degrees? Well, theta radians, if you multiply it by 180 and divide it by pi, that will give you theta in degrees form. And that's written right here. 360 degrees equals 2 pi radians. And so 1 radian equals 360 over 2 pi, which is 57.3 degrees. What's 360 over 2 pi? That equals 180 over pi, because 360 divided by 2 is pi. Okay, moving on to angular velocity. So at what rate is the degree changing at? So theta, if we divide it by time, well, theta is the distance and t is the time, and that equals our speed. Now remember, what does theta equal? We just said it here. Theta equals S over r. So theta over t, noting that theta equals S over r, meaning S over r over t is our angular velocity, and this is just the same as S over rt. So what does this mean exactly? We'll just divide theta by time to get its velocity, to get its speed. Remember our formulas, we have many formulas. V equals d over t, or V, just the d, we're not using the normal distance, we're using theta instead. Otherwise, d equals vt, just all formulas we're using now. And we're just subbing in what theta equals, which is this part right here. That's the angular velocity, the rate at which theta is changing at. And then what does it say here? The ratio of theta over t is the rate at which the angular displacement changes, and it's given by the simple W. W, actually this is omega. This is like the Greek alphabet or whatever. Okay, what they say here, the ratio S over t is the speed v around the circumference of the circle. That makes sense. Instead of looking at the speed of theta, we're looking at the speed of s, which is how fast we're moving along the circle if we divide it by t. S is the distance around the circle, S over t is the speed around the circle. Okay, and they just say here, W equals V over R, where V equals S over T. And if we sub it in to be sure, W equals S over T over R, which equals S over RT, which is the same thing we have before. So there's different ways of writing the same thing. Whatever, who cares? And what else? Oh, they just rearrange the formula. So W equals V over R it was. So they made, what did they do here? What did they do? Well, W, let's change the V out. It equals S over RT. What do they do next? The W and T are together, right? So let's multiply both sides by T times T times T. Here the T's will cancel out. So you're left with S over R equals WT. And what did we say S over R is? S over R equals theta. So you end up with theta equals WT. Alright, so just the same formulas over and over, just rearranging them. Whatever. And finally this thing right here. W equals 2 pi f. Well, what's f? If an object rotates around a circle at f cycles per second, then it moves 2 pi f radians per second. So remember, how many degrees do we have around a circle? 360 degrees. And if we convert that to radians, 360 times, how do we convert to radians? Oh yeah, times pi over 180. So times pi over 180. Well, what's 360 divided by 180? It's 2. So you end up with 2 pi. So we have 360 degrees around a circle, or 2 pi around a circle. So if we're looking at the speed at which we move around a circle, we call that f. Well, our speed in terms of radians is 2 pi f. How about our speed in terms of degrees? It would be W equals 360 f. right? Same thing. I don't know, there's more ways of writing the same thing, who even cares? And then what they say here, the relationship between the frequency in hertz and the angular velocity in radians per second is therefore this, where 1 hertz equals 6.28 radians. The heck? I mean, I don't know, keep that in mind. 1 Hz, I guess it's just another unit to memorize. They give you a formula sheet. I hope they write it down there, otherwise you might want to write it in your cheat sheet for the exam. This is something to remember. Okay. A juggler throws a bowling pin as shown in figure 3.2. What is the angular velocity of the pin and what will the angular displacement of the pin be at 0.9 seconds? Let's first figure out the angular velocity. So here we see the pin changes from 90 to 57, that's 33. From 57 to 24, that's another 33, and again 33. So it's changing 33 degrees every 0.2 seconds. So remember, we're looking for the angular velocity, that's W, and W equals V over T. Well, what's our V? What's the rate at which we're changing? We are changing 33 degrees every 0.2 seconds. And what's that equal to? Putting that in my calculator. 165 degrees. But remember, they like to put the angular velocity in terms of radians. So let's convert that to radians. So times pi divided by 180. And that gives me about 2.88 radians. Let's answer the first question. What's the second question? What will the angular displacement of the pin be at time 0.9 seconds? Okay, first off, I have to spoil the answer for this question because I don't like how they did it. Normally, this would just be multiplying W times 0.9. So angular velocity times how long it took. That gives us the displacement, remember, D equals Vt. But what they do for the answer is they measure it against the right horizontal. So normally we'd assume the angle starts from here, just like the pin, right? The pin starts from the bottom and it spins that way. But they assume the angle starts from here, from the right horizontal. And then like it's down at first, then it starts moving up eventually. I don't like this weird solution. But you have to note that a good question, or at least the bare minimum of the question, is to specify where the angle, where you measure it from, where's the starting point. Normally every question by default it should start from the true north, right? So pointing up, what does the angle change from here? Like this, like that, whatever. I don't know, for whatever reason I've never seen this before that went through the right horizontal. But yeah, whatever. Anyhow, moving on. Circular velocity and acceleration. What does this formula mean? You don't even need to look at the what am I talking about? What's 2 pi r? You should know this. 2 pi r is the circumference around a circle. And t, what's t? Well, they tell us the time taken. If an object travels around a circle once, the distance traveled is the circumference of the circle. The time taken is known as the period t of the motion. So t is just like normal time, but it's specifically talking about how long it takes for you to go around the circumference of a circle. And that velocity is our circular velocity. Before we had angular velocity, now we have circular velocity. How long does it take us to move around a circle? What's the distance? The distance is, of course, the circumference of the circle. And the time is how long it takes us to go all the way around. Okay, let's move on to this key concept. The velocity of an object in circular motion changes continuously since the direction in which the object is moving is changing continuously. That makes sense. Imagine you have your circle, right? If you're at this point and you're moving forward, you're pointing in this direction. If you're at this point, you're moving at this direction. If you're at this point, you're pointing at this direction. So your velocity is always changing direction, even if you have a constant velocity. What's the next key concept? If an object is traveling in a circle at constant speed, its instantaneous acceleration is always pointed exactly towards the center of the circle. This is a bit of a weird concept, but it actually makes sense if you think about it. What's velocity? Velocity is a vector, which is two things. What are they? It's a magnitude and a direction. Well, this vector, it has a constant velocity. This velocity has a constant magnitude. It has the same speed. What else is its direction? Its direction is constantly changing around a circle. So its acceleration needs to exist. It has to have acceleration because the direction is changing. And what's the acceleration pointing at? It's always pointing towards the center of the circle. Otherwise, this thing will just fly off. It will just keep going this way. It will just keep going that way. There's an acceleration that's pointing towards the center of the circle. so that this object can stay on the circle. Okay? Grabbing all this out. What else is there? Okay, and that acceleration, they found the formula for it, I don't know how, but that acceleration is v squared over r. I have no clue how they got that. What was v squared? Well, they gave it to us here. V is this, 2 pi r over t, the speed you go around the circle, or we had a different v before, right? We've got this other v. This v equals s over t, which is the same thing. S over t is 2 pi r over capital T. Because what's t? The time it takes you to go around the circle. And what's 2 pi r? The distance around the circle, the circumference of the circle, that is. And s can be 2 pi r if you've gone around the whole circle. And t can be capital T if you've, again, gone around the whole circle. There's different ways of saying the same thing. Okay? So this formula, don't forget it. That's the centripetal acceleration. And then what's this formula? Should be very obvious. Because what's this? Well, this is AC. And m is what? Well, m is just m. And what's the formula for F? F equals mc. So this is just a type of force. It's the centripetal force. Fc equals m times AC, where AC is v squared over r. Okay? What else? I don't care about all this. Okay, let's do this question. A 45 kilogram child is riding the roller coaster at an amusement park. A portion of the track is made up of 2 semicircular sections as shown in figure 3.4. One with a radius of 10 and the other radius 16. The roller coaster travels along this section of the track at a constant speed of 7 meters per second. In what direction is the child accelerating at point A, and in which direction is the child accelerating at point B? Let's look at the figure. Okay, so we've got this kid. What's his mass? I think it was 45. Whoops. Come on. 45 kilograms. Let me make sure. Yep. This one has radius 10, this one has radius 16. And finally, what was the speed? I should have checked that. The speed is 7 meters per second. So v equals 7 meters per second. Okay, they want us to find what direction is the acceleration pointing in for this child at this point. Well, as I said before, the acceleration is always pointing towards the center of the circle. Otherwise, he will just sort of fly away. He'll just keep going straight. He needs acceleration that's pointing him straight down. In this case, this force, this acceleration, what is it? It's actually the force of gravity. Because he's right there. And then at point B, again, just pointing straight at the center of the circle. So we know the direction. It's straight down for part A and straight up for part B. I guess, how does that make sense though, right? What's the acceleration that's pointing him up? Maybe it's like the force of the track. The acceleration of the track, maybe? I don't know. We just know it's pointing towards the center of the circle. Okay, what's the next part? If the child was on bathroom scales, what would they read in kilograms at point A? Okay. If the child was on bathroom scales, what force is that? When you go on the scales, what's that called? It's called your weight. And what's your weight? Your weight equals mass times gravity. But what forces are acting on this kid? There's 2 forces, right? There's the force of weight, and there's also one more force, the centripetal force. Fc equals m dot AC, right? The force that's causing him to go towards the center of the circle. And so we have to oh, right. Because the centripetal force, the weight would already be included in that. The weight would already be included in the centripetal force. So, wait, what am I trying to say? Okay guys, sorry, I confused myself. What do we know? We know weight equals mass times gravity. So 45, and let's say gravity is 10. So 45 times 10 is 450 newtons. And what direction does weight point in? It points straight down. What's our net force? Our net force is actually the centripetal force. That's the net force of everything we have. The net force is the centripetal force. And what's the centripetal force? Remember the formula, it's m times v squared over r. So m is 45 times what's v squared? It's 7 squared over r, which is 10. So we put that in calculator. 45 times 7 squared over 10. That's 220.5 newtons. And there's one final force, the one we're looking for is the force read from the bathroom scales. And that's actually the normal force. So F of normal, that's the normal force. I think I told you before, normal force had certain definitions. No, definitely the normal force. What the normal force is the upward push from the ground, from the surface. So in this case, it would be the roller cart, the cart, and at home it would be the bathroom scales. What I told you is before that that the weight is the normal force is because when you stand on the bathroom scales, what force is acting on you? There's the weight force down, and then the normal force straight up. So then in that case, the normal force equals the weight. In this case, we also have the other forces like centripetal force acting. So that wouldn't be the weight you would read from the bathroom scale. So we know our net force is 220.5, and we know our weight is 450 N. Yep. And we'll do the positive direction to be down, right? So the centripetal force is acting down, that's the positive direction. The weight force is acting down, that's also the positive direction. The negative direction will be the force pointing up, which is the force, the contact force, the contact normal force. And so that's the negative direction, so it's minus F of N. And that's the force you'd read, that's the weight you'd read when you're sitting on the bathroom scales without any other forces acting on you. So what's the normal force? Let's rearrange. Oh, we don't need to rearrange. Let's subtract 450N from both sides. Oh, no point of putting the N there. Subtract 450 from both sides. So you're left with negative 229.5 equals negative Fn. And then you multiply both sides by -1, so this one becomes positive and this one becomes positive. So that's the net, that's the normal force. Now we want to find the weight of the kid. So remember, the normal force is mass times acceleration, and we're looking for what are we looking for? Right, so on the bathroom scales, of course, it wouldn't display the force, it would display your weight. So you have to get rid of gravity. So 229.5, let's just say it's 230, we divide it by 10, and you end up with Fn equals 20. Oh no. The kid's weight at home would be 23 kilograms. So that's it, that's the example. This is the food formulas. Let's do part D. I was gonna skip it, but this was a bit all over the place. Let's do part D. What would they read in kilograms at point B? Okay, first let's find the centripetal force. The centripetal force is pointing up. Let's keep down as the positive direction. So pointing down is the weight, mg, and this kid weighs, the second kid, oh, it's the same kid. So 45 kilogram, what's the weight? Weight equals 450 newtons. Down is the positive direction. How about the centripetal force? That's pointing up, that's negative. The centripetal force, Fc, equals the mass, 45 times 7 squared divided by the new radius, which is in this case 16. This ends up being 137.8. And finally, we're looking for the normal force, which is pointing in the negative direction as well as pointing up. We're trying to find this. So remember, this one is negative, the centripetal force is pointing up, negative 137.8 equals gravity pointing down, positive 450, minus the centripetal force, Fn. Alright, now just solving for Fn. Let's subtract 450 from both sides. You end up with negative 587.8 equals negative Fn. Multiplying both sides by -1, you end up with this positive. And remember, for this final one, we have to divide by gravity, which is 10. and that equals about 59 kilograms. Okay, moving on. Summary, key formulas, we'll talk these out. So what were the formulas? They're all variations of the same one. Review them, make sure you understand them, check where they are in your formula sheet, and you should be good to go. Okay, moving on to statics. Statics is a study of stability in systems, fair enough. There's a bunch of different types of static equilibriums. A system is said to be in equilibrium when the net force on that system is zero and the net torque on the system is also zero. You have static equilibrium, dynamic equilibrium, stable and unstable. Review these definitions on your own time. I'm going to be moving on. Torque. Torque is very important. What is torque? Where is it? Yeah. The physical quantity which causes an object to begin to rotate or move in a circle, or more generally to change its rate of rotation, is a torque. It's rotating around a pivot. Suppose that an object to be accelerated into circular motion is attached to one end of a rod, the other end of which is attached to an immobile pivot or axle. Alright, so this is the object we're looking at, and this is the immobile pivot or axle. Suppose the rod is rigid, very light, we can know its mass, circular motion, linear force, okay, whatever. The formula for torque, what is it? The formula for torque is force, the one we already know, times d. What is d? The distance from the pivot. Generally, can't always be sure. And what is torque measured in? Newton meters. What the hell does that mean? Oh yeah, the moment. Whoops, moment. I have to explain what moments are. In physics, the word moment means the product or quantity of its perpendicular distance or from a given point. In the case of the moment of a force upon an axis, is the product of the force and the distance between the axis and line of action of the force. Such a horrible definition, right? This is the moment. It's basically another way of saying force. So if you have a seesaw like this, if a force was acting like this, that's one moment. And if a force was acting like this, that's another moment. That's what moment means. Very horrible definition, very horrible word. The torque provides us with a useful way to measure the turning effect of a force applied to a rod, which we call a moment, arm, or lever. What the heck? We should read this. Notice that the definition of torque at the beginning of the section and in equation 4.1 does not specify any particular spatial point as the pivot point or fulcrum. What a word, fulcrum, about which torques must be calculated. The axis of rotation is determined by the physical system, and the fulcrum is selected by us. It may be different from the axis of rotation. Now, let me skip this. Okay, very important. A torque might tend to turn a system in the clockwise or the counterclockwise direction. Moving on to the end, this condition is called the principle of moments. Very important definition to memorize. At equilibrium, the sum of clockwise moments equals the sum of the counterclockwise moments. So, what this equation means, the sum of the clockwise torques is equal to the sum of the counterclockwise torques. Best way to understand this is an example. Let's look at this one. So we're actually operating on just one side of the pivot. Normally you'd be looking at the other side, but here we're just looking at one side. And we assume this pivot is in equilibrium, right? So what's causing it to be in equilibrium? It's this torque acting in this is the counterclockwise direction, and this torque acting in the clockwise direction. So what's this torque equal to right here? Remember the formula for torque? It looks like this. Equals Fd. What's F? 10. And D is what? 0.4. Distance from the pivot. And that equals 4. How about the clockwise direction? It's 4.4 times 0.9, which equals, what does that equal? 4.4 times 0.9. 3.96. Oh, this 4 is meant to be repeating. Put in the calculator, it's 4.4444444 times 0.9, and you eventually get to 4. And they're equal. Right? They're equal. Try this on your own. Find this torque and that torque, and they should both be the same. Skip all this. Yeah, we'll move straight into examples. 3 people are sitting on a seesaw as in the diagram. The masses of the 2 people on the right are as shown, and as are their distances from the pivot. The third person is seated on the left and is a meter from the pivot. Given that the seesaw is stationary, what is the mass of the third person? Okay, so we've got 3 people shaped as balls for whatever reason. We've got this one here, and and this one on the left, and we're trying to find this person's mass. Okay, how can we find their mass? Where does mass come into the equation? Well, we know torque. Remember torque? Torque equals Fd. But do these give us mass? Yes, F gives us mass because F equals mass times acceleration. So we most likely need to find the mass of this bloke. I mean the force, the torque of this bloke. From there we can extract the force, and from there we can extract their mass. I guess they didn't give us acceleration in the question. Such a horrible Amjad. These examples are so bad. They're supposed to give you the acceleration. In this case, we're going to assume acceleration g equals 10. Okay, let's get started. Remember what we just learned? The clockwise and counterclockwise torques are the same. So we have this torque and this torque. And they have to be equal to this torque. Otherwise, these are called moments. So the sum of these two moments has to equal the moment on the left. Let's find this left moment. What's this left moment? Let's call it torque 2. Force times acceleration. What's the force? 300 times, not acceleration, times the distance, which is 1. So this one's 300. And the other one is 200 times 2. So 400. So the net torque on the right side is 700. What was the unit of measurement for torques? What was it? Let me check. Nm. What does that mean? I think. Oh yeah. Force is newtons and distance is meters. So Newton meters. Okay, that's fine. So we'll say this is Nm. What's the torque on the left hand side? It equals F3, which we don't know, times 1. What do we know though? F3, right, the torque on the left hand side, equals the torque on the right hand side, which we found to be 700. So now we know 700 is equal to the force on the left. Remember, that equals mass times acceleration. We're trying to find the mass. We just said acceleration is 10, gravity. So m equals 70.